Okay, so the Bohr atom, we should talk about the successes and failures, which is indeed what one of the sections in this chapter is called, but with the Bohr atom. The Bohr atom correctly predicts basic atomic structure, basic atomic spectra, and the Frank-Hertz experiment, which I'll describe in a second, verifies the basic Bohr model, but it's not perfect. We're still in imperfection land, and there's a couple of things that it doesn't describe correctly, or that we know needs to be corrected. And so we'll talk about some of these, and some of these we may not talk about. But one is that we need a reduced mass correction. What does that mean? We'll talk about that in detail later. But the reduced mass correction has to do with this fact that when we started talking about this, we talked about that we're assuming the nucleus stays in place and the electron goes around it. In reality, the center of mass of the nucleus and the electron, if it is anywhere other than at the center of the nucleus, if it's a little bit over here, if this is the center of mass, then in reality the nucleus goes around the center of mass and the electron goes around the center of mass. And the correction in the model requires what's called a reduced mass correction. You can correct that by effectively reducing the mass of the electron. We'll go over that maybe in a little bit of detail, because in actuality the nucleus moves. In the classical model, the nucleus moves. Another thing that's not predicted by the Bohr atom, which I talked about during the demo, was that it doesn't predict fine structure. So the atomic spectra, remember we had these kinds of emission spectra when you put energy into a dilute gas of hydrogen, in this case it's a little blurry, but mercury, sodium, lithium, that you get out a discrete spectrum of light. It's the fine structure that is not understood. Now, you can't really see in this kind of experiment, but the fact that this line here actually is made up of a couple of really closely spaced lines of slightly different color. And it's that fine structure that we're not able to predict with the Bohr atom. It predicts the energy levels between those quantum states, n equals 1 equals 2, n equals 3, but there's actually within each of those states, within the state with quantum number 1, there may be multiple substates. Within the state with quantum number 2, n equals 2, there may be multiple substates. And you've probably heard of, for example, electron spin, right? So you could have an electron which is in the spin up or an electron in the spin down. And so there's slightly different energy within a given state. And so those slightly different energies within a given state give us fine structure. So that isn't predicted by the Bohr atom. In addition, multiple electron atoms are not described correctly. Multiple electron atoms. We really just stuck with singly ionized helium, doubly ionized lithium, etc. Single electron atoms. Once you get additional electrons, one of the problems in something with additional electrons, let's say that we've got, it doesn't matter, some nucleus with number of protons Z, and so you got a bunch of electrons. One of the things that happens is something called shielding, that the electrons do not see the full charge of the nucleus because they are interacting with each other, right? That shielding effect can't be explained by the Bohr atom. Lastly, perhaps not last, but I think lastly, is that he didn't explain why the angular momentum is quantized. And in principle, we'll find that the Bohr atom is incorrect because there just are no such thing. There are no classical orbits. And we will find that quantum theory describes something somewhat different than classical orbits. So these are some of the issues with the Bohr atom. which does otherwise work quite well. So let's just look at some of the successes. Remember, in 1913, Bohr theorized this quantum orbit model of the atom, and in 1914, the Franck-Hertz experiment confirmed not only the quantized nature of the atom, but also the basic energy levels of the atom. We're not going to go into details of the Franck-Hertz experiment, but basically, the Franck-Hertz experiment took atoms. So the Franck-Hertz experiment is another one of the experiments that happens in a vacuum tube with an electron gun. It's another one of these pretty standard experiments. But it was the first experiment to really confirm this quantized structure of the atom. So this is the basic Franck-Hertz experiment, that you have a filament and a potential, that electrons, what color do we want our electrons to be? Let's make them orange here. Electrons are being accelerated in that direction. The electrons are being collected on this plate, and the current is being measured. And so we can increase the accelerating voltage. And if the tube was empty, and the accelerating voltage is between the minus and the plus is a grid, so the electrons can move through it and be collected on the plate on the other side. And if you look at, so I remember that an ammeter, A, measures current. A voltmeter, this is not a voltmeter. This is the other one is a voltage source, a variable voltage source. So I should have drawn it. I drew it wrong. In electronics, a circle would usually be a meter, whereas a variable voltage source should be like a battery with an arrow through it, like that. Okay, so anyway, so we can increase the potential, accelerating the electrons, and if we increase the potential, we should expect to see an increase in current. And so experimentally, indeed, they did increase the potential. You see an increase in current. But they introduced mercury gas into the tube. If mercury gas is in the tube, then the electrons have a chance of having interactions with the mercury gas. But what they found was that they increased the potential, they increased the current, and it went as if there was no mercury gas in the tube, except at a certain point, all of a sudden, it drops down, the current drops down. And then they increase the potential, and then at a certain point, the current drops down. And so what they're seeing is that the mercury atoms are not, the mercury gas are not absorbing the energy of the electron. They're not taking any energy away from the electron until you get to a certain energy. And then the mercury all of a sudden is taking away the energy from the electron. That's these points here, right? At that point, at the downswing, the mercury atoms are taking away the energy from the electron. That's the idea of the quantized atom, is that it can't absorb any energy until you get to an energy level difference between its ground state and its first excited state, or its first excited state and its second excited state, or whatever. And so they're actually seeing, this is pretty cool, they're seeing those excited states, those states get excited at certain electron energies, right? At certain electron energies, at this electron energy and at that electron energy, and then they went up to far. You can see the different states of mercury get excited. So this is evidence that the Bohr atom, the quantized energy states, is correct.